We continue with the discussion on anisotropic media. Let us discuss what we have been looking at. So, we are looking at plane wave solutions in anisotropic media, and we found that there are uniaxial media for which epsilon x is equal to epsilon y is not equal to epsilon z. This is uniaxial, and there are biaxial media in which epsilon x is not equal to epsilon y is not equal to epsilon z. And if all the three are equal, then it is isotropic. Now, in uniaxial, epsilon x is equal to epsilon 0 k x, and because epsilon y is defined as epsilon 0 k y, in uniaxial media k x is equal to k y is not equal to k z, and because the dielectric constant is square of refractive index, we define the three principal refractive indices as we are defined earlier. N x is equal to square root of k x, n y is equal to square root of k y, and n z is equal to square root of k z. This is general, and so for uniaxial media, n x is equal to n y, and this is called n o. This is called the ordinary refractive index, and n z is called n e, the extraordinary refractive index. In general, for biaxial media, n x, n y, n z are the three principal refractive indices. For uniaxial media, n x is equal to n y, it is called n o, the ordinary refractive index, and n z, which is the third refractive index, is called n e, the extraordinary refractive index. Now, what we did was we looked at propagation of plane waves, and we found an eigenvalue equation which contained the E vector and the refractive indices. So, for a given propagation direction, which means kappa cap direction, I have to solve those three equations to get the values of n. I will find two values of n, which is called the two principal refractive indices, two eigen refractive indices, and corresponding to those refractive indices I will find two electric vectors, two displacement vectors which will correspond to that waves. So, these are two modes, eigen modes of propagation. So, for every direction of propagation we will have two eigen modes. The d vectors of those two eigen modes will be perpendicular to the k vector of the propagation, and the corresponding d vectors will give me the corresponding E vectors and everything, all vectors will be defined. So, for every propagation direction, which means for every kappa cap direction or for every k vector direction, I will find two eigen solutions corresponding to two refractive indices and two polarization states, and both polarization states are linear. So, as an example, first one we looked at is if I propagate along the z axis. Now, let us also recall that the x y z axis we are looking at is a principal axis system in which the epsilon tensor is diagonal. Off diagonal elements are 0 in this coordinate system. So, if my propagation direction is k along the z direction, we got two solutions. The first solution with an electric vector pointing along x, the corresponding displacement vector also pointing along x, because if E is along the principal axis, the d vector is also along the principal axis, and because E is now perpendicular to k, S is also perpendicular to d, and S and k are parallel. So, the energy propagation direction and the wave propagation directions are superposed, they are the same, E and D are parallel to each other, and the refractive index of this wave was square root of kx. This is one solution. The second solution we obtained is propagation along z direction again. So, if I call this y, the E vector is along y, D vector is along y, and S vector is also parallel to k now, with a refractive index which is square root of ky. This is one eigenmode, this is another eigenmode. This eigenmode propagates with a refractive index n is equal to square root of kx. This eigenmode propagates with a refractive index n is equal to square root of ky. So, the velocity of this wave will be, the phase velocity of this wave will be square root of c by square root of kx, and the phase velocity of this wave will be c by square root of ky. Now, note that in uniaxial media kx is equal to ky, and so both velocities are equal. So, this is a special direction in uniaxial media in which the two eigenmodes have the same velocity of propagation, and this is called the optic axis. If you have a biaxial medium, kx is not equal to ky, and so the velocities of the two waves are different. Now, Mohit, you had a question. Okay. So, this in these two modes, the S vector and k vector are parallel to each other, and E and D are parallel to each other, and I have one x polarized mode. So, the propagation is like this: one x polarized mode travels with velocity c by square root of kx, the y polarized mode travels with the velocity c by square root of ky, and so these are two eigenmodes. If you consider any other polarization state propagating along this direction, I would have to break it up into the x eigenmode and the y eigenmode. The x component will propagate with this velocity c by square root of kx, the y component will propagate with a velocity c by square root of ky, and if the velocities are unequal, then they will have an additional phase difference, and so the polarization state will change as it propagates. But in uniaxial media, because kx is equal to ky, the two velocities are equal and the propagation will not change the polarization state, and that is the special direction called the optic axis, and in uniaxial media there is only one such direction. If kx is not equal to ky is not equal to kz, that means in biaxial media there will be two directions where this will happen. The two eigenmodes will have the same speed, they are not coincident with x, y or z, it is some other direction. There are two other directions in which the velocities of the two eigenmodes will become equal, but we will not look into more details of biaxial media, but we will concentrate more on uniaxial media. The second case we looked at is when you have a propagation in the xz plane. So, the k vector makes an angle psi with z axis. So, in uniaxial it is making an angle psi with the optic axis. Z axis is the optic axis, this is called this is also the optic axis. So, it makes an angle psi with the optic axis. We found two solutions. The first solution was, so let me draw the figure here again here. So, this is z, this is k vector psi, this is x. One polarization had an E vector like this along the y direction, D vector also parallel to the y direction, because when E is along principal axis, D is parallel to E, and then S vector is also like this. And the refractive index seen by this wave is square root of ky, and for in uniaxial media it is NO. And this refractive index is independent of psi. So, this wave propagates as if it is propagating in an isotropic medium, in which the refractive index or the velocity is independent of the direction of propagation. In an isotropic medium, no matter what direction I propagate, the refractive index is the same, the velocity is the same. So, this particular polarization propagates with the same velocity c by NO irrespective of the angle psi that you make with the optic axis. This is one particular polarization. Note that this polarization is perpendicular to the k vector and to the optic axis. So, if I restrict myself to uniaxial media, this is the optic axis, this is the propagation direction. The propagation direction is in the xz plane. This polarization, which means the d vector of this wave, is perpendicular to the k vector and z vector and the z direction, which means the optic axis. So, the ordinary wave or ordinary polarization, this is called the ordinary polarization, is perpendicular to the optic axis and to the propagation direction represented by the k vector. The only angle I need to specify is psi, because epsilon x is equal to epsilon y, there is complete symmetry in the x and y directions. So, no matter what orientation I propagate, as long as I make an angle psi with the optic axis. Suppose my optic axis is like this, if I propagate at 30 degrees to the optic axis here, or 30 degrees here, or 30 degrees here, the refractive index will be always NO for this particular wave, which is called the ordinary wave. And so, if my propagation, suppose my optic axis is here and propagation is here, this polarization has to be perpendicular to the optic axis and k vector, and it will be like this. So, this will propagate like this polarization, and the k vector and s vector of this wave are parallel to each other. The behavior is very similar to an isotropic medium, and hence the name ordinary refractive index. The other solution that we obtained was this is z axis, this is x axis, this is k vector again. Note that no matter what direction I propagate, no matter what medium it is, d is always perpendicular to k vector. So, we found the second solution to have its d vector in this plane. So, if this is psi, we found this to be psi, and depending on, so this is s vector, this is the e vector. So, if this is theta, this is also theta. Because the d vector is not along the principal axis, e vector and d vector are not parallel to each other, and hence the s vector, the pointing vector, and the propagation vector k are not parallel to each other. The velocity of this wave satisfies this equation. So, let me put a subscript here, just to I will explain this. Ne square of psi is equal to cos square psi. Remember, you had kx, which is NO square, plus sin square psi by kz, which is Ne square. Please note, NO is by definition square root of kx is equal to square root of ky, and Ne by definition is square root of kz. These are constants of the medium, they do not depend on the propagation direction. If I give you a medium like lithium niobate, which is a very important uniaxial crystal, I can give you the value of NO and Ne for a particular frequency or a particular wavelength. This Ne has an Ne of psi. This E stands for, this E subscript E is for extraordinary wave. This solution corresponds to an extraordinary wave, and the velocity of this extraordinary wave depends on psi through this equation. For this wave, the s vector and k vector are not parallel, and hence the name extraordinary. It is not like an isotropic medium, it behaves in a different fashion, and so it is called an extraordinary wave. And Ne of psi, please differentiate Ne of psi and Ne. Ne is a constant, Ne of psi, when I write, it means the refractive index as seen by the extraordinary polarization when it propagates with its k vector, making an angle of psi with the optic axis. This is the optic axis, this is the optic axis, k vector makes an angle psi with the optic axis. The first solution has its polarization along y and has a refractive index NO independent of psi called the ordinary wave. The second solution has a refractive index depending on the angle psi according to this formula, and it is called an extraordinary wave and has its S vector and K vector not parallel to each other. So, this equation gives me the refractive index as seen by the extraordinary wave, which is now a function of psi, and as you can see from here, if psi is equal to 0, then the propagation is along the optic axis and NE of psi becomes NO, and that is the definition. The optic axis is the direction when the refractive index seen by the ordinary wave and the extraordinary wave become equal. If psi is 90 degrees, then I propagate perpendicular to the optic axis, then NE of psi becomes NE. So, NE is the refractive index of the extraordinary wave if it propagates perpendicular to the optic axis. So, if I propagate perpendicular to the optic axis along x, one polarization will be y, which propagates with the refractive index NO, the other polarization is z, propagating with the refractive index NE. So, note that the maximum difference of velocities between ordinary and extraordinary waves will appear when you propagate perpendicular to the optic axis. At any other direction, the value of this quantity will be between NO and NE. So, maximum difference, if you want a maximum difference between propagation speeds between the ordinary and extraordinary waves, you need to propagate perpendicular to the optic axis for a uniaxial medium. So, I leave it to you to find out what direction should I propagate. Suppose I give you Nx, Ny and Nz. What is the direction? Suppose I give you Nx, Ny and Nz values, say Nx is less than Ny is less than Nz. So, let me assume. Then what direction should I propagate to maximize the difference in speeds between the two polarization states? Sorry, is y direction, because Nx and Nz, as I have defined, Nx is less than Ny less than Nz. So, when you propagate along y, one will be Nx, the other will be Nz, and that is the maximum difference that you can get in the medium. Also note that for the ordinary wave, S and K are parallel, but for the extraordinary wave in general, if you do not propagate along the optic axis or perpendicular to the optic axis, then S and K are not parallel. So, as I showed you on the first day, you will have a wave front looking like this. The wave front is along this direction, along this K vector direction, but the energy propagation direction is oblique. So, the wave front is looking this direction, but it is propagating like this. The energy is propagating obliquely, and this is the reason for what is called as birefringence in certain crystals. If you can use these certain crystals to see, for example, double images. So, this is a normal isotropic crystal, sodium chloride, and that is an anisotropic crystal, calcite. So, you can see two lines, two images coming through this. Because light is unpolarized, it comes out through the crystal. One of these lines corresponds to the ordinary wave and the other one corresponds to the extraordinary wave. The refractive indices of the crystal are different for the ordinary and extraordinary waves. So, the refraction inside the crystal and refraction outside the crystal is different, giving you two images, and that is called birefringence, because there are two refractive indices, and this particular property is used in constructing many polarization devices like half wave plates, quarter wave plates, and so on. Now, I want to just give you one problem, and that is, suppose I have this equation, please remember we have written this equation d is equal to epsilon E, and epsilon is assumed to be in the principal axis system. Now, what will happen if I rotate my coordinate system and go to another system? So, let me give you a simple problem. So, let me look at x and y, x y coordinates. So, this is x and y. This is a principal axis system. Suppose I rotate the coordinate system around the z axis and go to another coordinate system x prime y prime. Suppose this is theta. What is epsilon in this coordinate system? Let me call it epsilon prime. How does the epsilon matrix transform itself when I change my coordinate system? Okay. And I want you to show that if the medium is uniaxial, which means if epsilon x is equal to epsilon y, the epsilon matrix will remain the same. in general, if epsilon x is not equal to epsilon y is not equal to epsilon z, then this rotation changes the epsilon matrix. It may no more remain diagonal, but if it is a uniaxial medium with epsilon x is equal to epsilon y, the epsilon in the x y z coordinate system and the epsilon in the x prime y prime z coordinate system are the same. And that is why I said this equation is the most general equation for extraordinary waves in a uniaxial medium, because as I told you, if you give me a principal axis system and if you say I propagate like this, suppose this is z axis x, y and z. So, if you say I propagate like this, I will rotate my coordinate system such that my k vector lies in the xz plane, and epsilon in this coordinate rotated coordinate system and the original system are the same. This is what I have asked you to show. So, all that is important in a uniaxial medium is what is the angle made by the k vector with the optic axis. So, the conclusion of all this analysis is simply the fact that if I take a uniaxial medium with optic axis like this and propagation in some arbitrary direction, I have two eigenmodes. The first eigenmode, called the ordinary wave, has its d vector perpendicular to the optic axis and k vector. Look at this solution, this solution. This is the ordinary wave. The E vector and d vector of this wave are perpendicular to the optic axis and to the propagation direction, k vector. The refractive index as seen by this is always NO, independent of psi. The second solution is an extraordinary wave with its d vector lying in the plane containing the optic axis and the k vector, and the refractive index as seen by this wave satisfies this equation. So, if I give you a medium and I tell you NO is so much, NE is so much, and if I say I propagate at 30 degrees to the optic axis, you can find out what is the velocity of this wave. So, please just show this, because these you can derive this from the transformation properties of the vectors D and E vector. You know how vectors transform on rotation. So, using this transformation you can find out the transformation of epsilon tensor. Okay. Also, please note that these refractive indices are functions of frequency, which is called dispersion. The ordinary index changes with frequency, the extraordinary index itself changes with frequency. So, how does the refractive index vary? If I increase the wavelength, will the refractive index decrease or increase? Normally decrease. As you increase the wavelength, the refractive index decreases, which is called normal dispersion. So, NO and NE, both of them will have dispersion, both of them will have frequency dependent values, and so this needs to be kept in mind, because when we look at nonlinear interactions, we will look at different frequencies, and the NO and NE values are themselves functions of frequency. Here, please note that there is an angle between k and s vector. Let me call this alpha. So, alpha is theta minus psi. Now, under what conditions will alpha be 0? For what values of psi is alpha 0? 0 and pi by 2. If psi is 0, I propagate along the optic axis, k and s are parallel. If psi is 90 degrees, k and s are again parallel, and in between alpha is finite. So, there must be a value of psi at which alpha must be maximum, right. So, what I would like you to do is please find out the angle alpha. The information you have is, for a given psi, d vector makes an angle psi with the x axis. If k vector makes an angle psi with the z axis, d vector makes the same angle psi with the x axis. The d vector and E vector are related through d is equal to epsilon E. So, you can find the direction of E vector. If you know the direction of E vector, you know the direction of S vector, because S vector is perpendicular to E vector. So, you can find out psi theta. So, if you know theta and psi, you know alpha, So, what I would like to do is to find out an estimated value of alpha. So, just for us to know what these numbers are. So, let me give you a specific example. Let me take lithium niobate as an example. Li lithium this is LiNbO3. This is a very important medium in optics. Just like silicon is in electronics, this has a very high nonlinear coefficient. It has a very high acoustoptic coefficients. It has a very high piezoelectric coefficient. It is a very, very interesting crystal, very nice crystal, and it is transparent somewhere around from 350 nanometers to about 4 microns or so. It is a huge transparency band, and it is used in many applications. So, let me give you at some specific wavelength. The ordinary index is given by 2.297 and extraordinary index is equal to 2.208. Okay, so, in uniaxial crystals you can have NO more than NE or NO less than NE. If NO is less than NE, the ordinary wave will travel faster than the extraordinary wave always. The extraordinary wave refractive index varies between NO and NE. The ordinary wave always has a refractive index NO. So, if the crystal has NO less than NE, the ordinary wave is always travelling faster than the extraordinary wave, and such a crystal is called a positive uniaxial crystal. Just by convention, positive uniaxial means NO less than NE with the ordinary wave travelling faster than the extraordinary wave. If NO is more than NE, the extraordinary wave travels faster than the ordinary wave, and the crystal is called negative uniaxial crystal. So, this is an example of a negative uniaxial crystal, and you can see the difference. The difference is not very large, it is about 0.09. It is a strongly anisotropic crystal, and this difference will lead you to a difference between K and S vector. So, what I would like you to do is say take psi around 45 degrees and try to find out what kind of values of alpha you will get. Is it tenths of degrees or is it a fraction of a degree or what numbers are these, and why don't you try to find out what is the value of psi at which alpha will be maximum. There must be some value of psi, some propagation direction K vector where I will get maximum difference between the S vector and K vector. That means maximum difference between the propagation direction of the wave front and the energy. Okay. Now, what I want to introduce is another very important concept before we go to the nonlinear effects, and this is called index surfaces. In anisotropic media, actually if you go through some books, you will find a lot of surfaces. There are ray surfaces, there are index surfaces, there is optical index, ellipsoid, etc., a lot of surfaces. So, when you look at a surface in a book, you need to be careful to find out what is it representing. Now, this is called an index surface. It is a plot of refractive index variation of the ordinary wave and the extraordinary wave as a function of angle. So, if I plot a figure, so for example, this is the figure which I want to plot, this is z axis, this is x axis. Remember, psi is the angle made by the K vector with the optic axis, and here this is the optic axis. I am looking at uniaxial media, so this is the optic axis. So, I want to plot how the refractive index of the ordinary wave changes as I change psi. So, I will take that means the distance from here will represent the refractive index of the wave as seen in that direction. So, suppose I propagate like this in this direction, what will be the refractive index seen by the ordinary wave? NO. So, I plot a point here NO. What about different other directions? It is always NO. The ordinary wave always sees the same refractive index NO no matter what angle I propagate. So, what is the surface I will get? What is the curve I will get? I will get a circle. This circle will have a will have a radius of NO. All that means is if you propagate in different directions, the distance from the center to this curve is the refractive index seen by that wave. So, this is the ordinary index surface. I must plot another one for the extraordinary index surface. And remember, the extraordinary refractive index has a formula like this as a function of angle. What is this equation? It is the equation of an ellipse. Any of psi versus psi is the equation of an ellipse with the two major, semi-major and semi-minor axes NO and NE. So, please I leave it to you to show that this is the equation of an ellipse, and so I will get an ellipse. Now, the question is, how will the ellipse be sitting with respect to the circle? Will the ellipse touch the circle at any point? Where? On the z axis. So, here and here the ellipse will touch because any of psi will become NO if psi is equal to 0. Will the ellipse lie inside the circle or outside the circle? Depends on NO and NE. So, suppose I take a positive uniaxial crystal. So, positive means let me plot for positive. Positive means NO less than NE. So, the ellipse will be lying outside. So, it will be like this. So, this distance is NE. So, this is the extraordinary this corresponds to the extraordinary wave, this is the ordinary wave. Because of symmetry in the x and y directions, the index surface can be obtained by revolving this curve around the z axis. So, you will get a sphere for the index surface of the ordinary wave, you will get an ellipsoid of revolution for the index surface of the extraordinary wave. These are the intersections of these two surfaces with this plane xz plane. In uniaxial media, because epsilon x is equal to epsilon y, you can obtain the index surfaces by revolving this curve around the z axis. So, you will get a sphere for the ordinary wave surface, index surface, and you will get an ellipsoid of revolution for the extraordinary index surface. So, all this means is if you propagate in this direction, the refractive index as seen by the ordinary wave with this distance, the refractive index as seen by the extraordinary wave with this distance. That is all it means. It is just a figurative representation of the two equations for the ordinary surface and the extraordinary indexes. Please note that these numbers are frequency dependent, NO and NE are frequency dependent. So, if I plot the index surfaces at different wavelengths, they will have different sizes. The radii of the circle and the ellipse will be different at different frequencies, and we will use this representation to understand certain features in the nonlinear interactions. Okay, so that will sort of complete our discussion on anisotropic media, because we will primarily be using the fact that I have two refractive indices that are available to me in an anisotropic medium. One of the refractive indices is controlled by this angle psi, because for nonlinear interactions I will see that I need to satisfy some conditions for efficient generation of new frequencies, and that will need some kind of a dependence of refractive index, some more refractive index values, and I can use this NE depending on psi to achieve this efficient interaction process. And we will use these index surfaces plots to understand some of those characteristics. Okay, do you have any questions in anisotropic media? Otherwise, I will introduce the concept of nonlinear polarization and look at some nonlinearities. Yeah. Okay. So, let me start looking at how do I introduce this nonlinear nonlinear optics essentially. So, remember we wrote this equation P is equal to epsilon 0 chi e. This is for a isotropic medium if chi is a scalar. If chi is a tensor, in anisotropic medium the same equation will be P is equal to epsilon 0 chi tensor into E. Chi would have in the principal axis system the 3 diagonal elements which may not be equal to each other. For uniaxial, 2 of the first 2 elements will be equal, the 1 1 and the 2 2 elements will be equal, and in a biaxial all 3 elements will be unequal. In component form, how do I write this equation? I can write this as P I is equal to epsilon 0 chi I j E j, where I am assuming summation over repeated indices. Because j is repeated on this side, this is a short form of this equation epsilon 0 j is equal to 1 to 3. Now, if you this is an equation representing the medium, this is not the this is please remember this equation when I write d is equal to epsilon 0 e plus p is the definition of the displacement vector. There is no approximation in this. This is an approximation. This is relating how the medium responds to an applied electric field, and this approximation is a linear approximation. I have retained terms up to E. Now, if you go back and look at the how do I derive a microscopic theory or expression for chi, you represent the atomic dipoles as harmonic oscillators and obtain this expression under the approximation that the displacement of the dipole is very small and the oscillation is harmonic. This is true as long as the electric fields are not very large. When the electric field becomes large, comparable to the interatomic electric fields in the medium, then this approximation fails. The oscillators are no more harmonic. So, the restoring force is no more proportional to displacement, and I need to modify this equation, and that is where the concept of nonlinearity comes in. So, instead of this equation, what I will have to write is, for example, so let me write here P I is equal to epsilon 0 chi I j E j, and I will have additional terms like, for example, epsilon 0 chi I j k. So, let me write a 2 here to represent it is a second order term E j E k plus epsilon 0 chi I j k l, this is third order term E j E k E l plus etcetera. There is supposed to be 1 here which is not written. If I do not write 1, it is a linear susceptibility. This is the linear susceptibility. This is called the second order susceptibility because P is proportional to E square. This corresponds to third order susceptibility, P is proportional to E cube, and so on. So, I must replace this equation, which is a linear equation, by this once the electric fields inside the medium become strong. So, if I take a light wave with a sufficiently high intensity value, the electric fields of that light will be strong, and I will start to see effects of these terms in my analysis. So, this term is proportional to E square, leads to second order effects. This term is proportional to E cube, it leads to third order effects. Second order effects include things like second harmonic generation, which means I launch a light of frequency omega inside a medium, and this term can lead to the generation of light of frequency 2 omega, second harmonic. If I launch two waves of frequencies omega 1 and omega 2 inside a medium, because of this term I can generate omega 1 plus omega 2 and omega 1 minus omega 2 frequencies. So, I can generate some frequency, I can generate different frequencies, and this term so leads to all kind of second order effects in which two frequencies can get mixed up. Remember, in linear case, if E has a frequency omega, P will also have a frequency omega only, it cannot have a new frequency. But because of this term, because of this product here, if E has a frequency omega, this E square can have a frequency 2 omega, and that leads to the generation of second harmonics, some frequency, etc. So, these are called the second order effects. This leads to the third order effects. Yes? What is? Oh, this is the kth component of E vector, where j, k, l go from 1 to 3. So, this is actually a shortened form of this equation. So, P I, the ith component of the polarization is sigma epsilon 0 chi I j E j sum over j plus sum over j sum over k epsilon 0 chi I j k 2 E j E k plus sum over j sum over k sum over L epsilon 0 chi I j k L 3 E j E k E L. So, this could be E 1, E 2, E 3, which is E x, E y, E z. So, j is equal to 1 is x, j is equal to 2 is y, and j is equal to 3 is z. So, this will have terms like E x, E y, E z, E x, E x, E x, E z, E x, E x, E y, all kinds of combinations. So, the point is, what is happening is, the linear expression told me that P only depends on E linearly, but when the applied electric fields become strong, then I can have additional terms in this expansion. That means, P I can depend on product of two electric fields E j, E k. Similarly, with the third order effects, I can have products of three electric fields. These lead to what are called as second order effects. So, this is what we will normally write. We will assume repeated indices are summed over. So, E j is summed over, k is summed over, L is summed over from 1 to 3. J is equal to 1 is x, j is equal to 2 is y, j is equal to 3 is z. Similarly, k is equal to 1 to 3, L is equal to 1 to 3. Okay. So, this is called the second order susceptibility, third order susceptibility. The third order terms, yes.
Can we observe these nonlinear effects in the isotropic medium?
Okay. Can we observe these nonlinear effects in isotropic medium? It will depend on this matrix. Now, let me tell you, I will show you later on this particular, how many elements are there in chi I j k? 3 into 3 into 3. I can go from 1 to 3, j can go from 1 to 3, k can go from 1 to 3. So, 27 elements. If your medium possesses a center of inversion symmetry, all chi I j k element, chi I j k 2 elements are 0. Media possessing center of inversion symmetry, what is the meaning? I position myself at a point, I replace all atoms with coordinates x, y, z by minus x, minus y, minus z. So, I take this atom, put it here, take this atom, put it there, take this atom, put it here. Okay? I replace all atoms with coordinates x naught, y naught, z naught by minus x naught, minus y naught, minus z naught. I get a new medium now. If this medium is the same as the first medium, this medium possesses a center of inversion symmetry. If the medium possesses a center of inversion symmetry, all 27 elements of chi I j k 2 are 0. So, this medium will not exhibit second order nonlinear effect. There are cubic crystals which have a non-zero chi I j k. Okay? There can be crystals which are not cubic, isotropic. There are isotropic crystals, which means chi I j is a scalar, but chi I j k is non-zero. Gallium arsenide is a material in which this is finite. But if you take for example an amorphous medium like glass, it is completely amorphous. So, this is not there in glass. You cannot have a second harmonic generation normally in a glass medium. There is no such restriction in the third order term. This is present in all media, whether it is a gas or a liquid or a solid, this is present always. So, glass will possess this, water will possess this, there are materials which possess this, all materials will possess this, but materials which have this strongly, actually this starts to affect the propagation much before this one, because these are actually, it's like a perturbation expansion, and each the next term is supposed to be smaller than the earlier term. Okay. So, when you take light propagating through an optical fiber, it is made of glass. So, this is not there, this is the first term that appears, and this controls how light propagates through an optical fiber over long distances. Now, this leads to things like what I have defined in the course, self phase modulation, cross phase modulation, etc., which means this will, as I will show you, this term leads to a change of refractive index depending on the intensity of the light wave. I am sorry, depending on the intensity or electric field of the light wave, the refractive index of the medium will change. This will lead to generation of mixing of 3 frequencies now. You see, there are 3 electric fields here multiplied. So, there are 3 frequencies getting mixed, so etc. So, we will come to this, but this is the expansion. So, first what we will do is we will discuss this, the effect of this term, and then once we finish this discussion, we will go into this term. So, second order effects will, which is what first we will discuss, and in second order effects we will look at second harmonic generation, called SHG, sum and difference frequency generation, and something which is very interesting called parametric interaction. You can actually amplify light using this process, and the optical parametric oscillator, which is a very important coherent source, uses this 3-wave interaction to generate light at new frequencies. So, these effects can help us to generate light at new frequencies given one particular frequency. If you give me a red laser beam with 800 nanometer wavelength, the second harmonic will give me what wavelength? 400. Wavelength will get halved as frequency gets doubled. So, I can generate a blue laser out of a red laser. You may have seen green laser pointers, and some of them have a red laser followed by a nonlinear crystal which converts the red into green, and that is a very easy way to convert light from between one wavelength to another wavelength, but of course, you need to satisfy some interesting conditions that we will discuss. Okay. Now, before we go into analyze this, let me look at what is the effect of the second term by taking a scalar equation. What this equation tells me is P is proportional to E square, some product in terms of Ex, Ey, etc. But for the moment, to get a physical understanding, let me look at this following equation. Suppose P is equal to, normally I would have written P is equal to epsilon 0 chi E plus, let me write this as some epsilon 0 into chi 2 E square. Let me look at a scalar equation just to understand what is going to happen. Yeah.
So, this media is converting this red light to blue or red to green.
Yeah.
So, there is an energy change in the phase.
Yes.
I mean, lower energy to higher energy.
Yes.
So, is the material going to suffer some sort of change to this conversion?
Okay. So, question is, when I convert from red to blue, the frequency has increased. So, the energy of the photons has increased. The material does not do anything other than helping in converting from omega to 2 omega. So, if you are able to convert all the input red light to the corresponding second harmonic, the energy that you are inputting is equal to the energy that is exiting. So, what does it mean? Number of photons. So, if you have 10 to the power 10 photons incident in the crystal corresponding to 800 nanometer, there will be half of 10 to the power 10 photons coming out at the frequency at the wavelength of 400 nanometers. So, there is complete energy conservation. So, number of photons is not being conserved. I am not conserving the number of photons. There are, so, what as you will see as you look at the picture, 2 photons at frequency omega actually merge to form one single photon at frequency 2 omega that comes out. So, there is the medium only helps in this process of conversion, it does not absorb or give any energy. It is a completely reactive system, it just allows this interaction to take place, and this is what I will show you why this, how this happens here. Okay. So, there is no, the medium does not give any energy from itself or does not absorb any energy. Okay. So, let me look at this equation. So, let me take okay, before I do this, please note now that because the equation is nonlinear, I should not use complex expressions, because as I told you in the beginning, the sum of real parts of two complex numbers is equal to the real part of the sum of the two complex numbers. But if I take products, that is not true. The real part of the product of two complex numbers is not equal to the product of the real part of the complex numbers. So, all the time I need to use real electric fields, real polarization, real etc., but we will still use complex by a judicious choice of the expressions, as we will come to that later. So, let me assume I have an electric field of the type E is equal to E0 cos k z minus omega t. It is a wave going in the z direction in the medium, and it has an expression cos k z minus omega t. So, what is the polarization that I will generate? Epsilon 0 chi E 0 cos k z minus omega t plus epsilon 0 chi 2 E 0 square cos square k z minus omega t. Now, let me express cos square theta in terms of cos 2 theta. Okay. So, this will be epsilon 0 chi E 0 cos k z minus omega t plus what is cos square theta? Cos 2 theta is 2 cos square theta minus 1. So, this is half epsilon 0 chi 2 E 0 square plus half epsilon 0 chi 2 E 0 square cosine of 2 times k z minus omega t. I have written cos square k z minus omega t as half of 1 plus cos 2 times k z minus omega t. Now, recall what is polarization. Polarization is dipole moment per unit volume. So, this polarization represents dipoles. This term gives me polarization oscillating at frequency omega. This term represents a polarization independent of time. So, if a medium has a time independent polarization, what does it mean? If you polarize a dielectric, there is accumulation of charges on the sides, on the surfaces. So, this will lead, this term will lead to an accumulation of charges on the surfaces of the crystal. This term is called optical rectification. It is like a rectification process in electronics, where starting from omega, you have launched the light at frequency omega, and you have generated a constant polarization term, which corresponds to a displacement of charges, which does not vary now, it is constant. The last term has a frequency 2 omega. So, this polarization now has a 0 frequency component, a component at frequency omega, and a component at frequency 2 omega. And because polarization are dipoles, oscillating dipoles, this means that now the dipoles are oscillating not only at frequency omega, but also at a frequency 2 omega. It is a combination, they are oscillating in a combination of 0 frequency, omega frequency, and 2 omega frequency. And when the dipole oscillates at frequency 2 omega, it will generate radiation at frequency 2 omega. because oscillating dipoles radiate electromagnetic fields. So, this particular term immediately tells me that because of the chi 2, there is a component in the polarization oscillating at frequency 2 omega, and that oscillation at frequency 2 omega will now generate electromagnetic waves at frequency 2 omega, and that is the origin of the second harmonic which comes out of the crystal. It is this term of the polarization which is responsible for the generation of 2 omega from the medium. If you take, for example, E is equal to E 1 cos k 1 z minus omega 1 t plus E 2 cos k 2 z minus omega 2 t. That means, if your light wave has two frequencies omega 1 and omega 2, propagation constants k 1 and k 2, if I substitute into this equation, what will I get? I will get the product of these two cosines in the nonlinear term, and those product can be written as cos A plus B plus cos A minus B. So, you will have one term at frequency omega 1 plus omega 2 and one term at frequency omega 1 minus omega 2. So, the component of polarization at omega 1 plus omega 2 generates some frequency, the component of polarization corresponding to omega 1 minus omega 2 generates the difference frequency. So, this particular term is responsible for the second harmonic generation, some frequency generation, difference frequency generation, and this is what we will study in more detail. So, the problem we will have to address is under what conditions will this process be efficient. Suppose I launch 1 milliwatt of red light, how many nanowatts or microwatts of power of the second harmonic will I generate? How do I maximize this conversion process, and what is the efficiency of this process? So, this is what we will address in the next class, and what I will do in the beginning is have a brief discussion of this tensor which is sitting here. It is a 27 elements tensor here. We will use some interesting concepts of contraction of indices and reduce this matrix of 27 elements to 18 elements, and as I will show you, many elements are 0 in materials, etc. And we will, starting from this equation, we will go back to Maxwell's equations and analyze the problem of generation of second harmonic. Okay, so is there any question? Yeah.
So you said that in media that are that can be center inverted, there will be no second term.
Yes, all elements chi I j k 2 are 0.
So why is that necessary?
I will discuss that next class. I will tell you that if the medium possesses a center of inversion symmetry, okay, if the medium possesses center of inversion symmetry, if I reverse the direction of electric fields, it is the same as before, right, because there is center of inversion symmetry. So, P will also get reversed over sign. So, if I change the sign of E j and E k and change of sign of P, then unless chi I j k is 0, I cannot satisfy this equation. So, it is just the fact that inversion symmetry means immediately that all elements must be 0.